You know what really keeps astronomers up at night? It's not asteroids or black holes, or even the mind-bending fact that most of the universe is invisible to us. What actually haunts them is precision where there shouldn't be any. When something from the void shows up, moving with the kind of accuracy you'd expect from a satellite someone launched on purpose, that's when things get weird. That's when people start to sweat. And that's exactly what happened when 3IATLAS blew past Earth in late 2025, not even slowing down to take a peek. The silence after was almost oppressive. Here was this object. Nobody knows how long it's been out there, drifting between the stars, covering distances our brains can barely process, and it just slipped past Earth like we were nothing. No little coarse tweaks, no turning to scan us, no heat signature, no sign it was listening or looking. Just a cold, straight shot right by the only place in this whole solar system where technology and intelligence have popped up, headed for Jupiter with the kind of exactness you can plot on a chalkboard. That total indifference, like we didn't matter at all, might actually be the most unsettling thing we've seen so far. Let that sink in. Picture it. You're driving across a strange country, following a route to a far-off city. You roll through little towns, maybe don't even notice them. Then you hit major cities, places you'd expect any traveler to at least glance at. In this analogy, Earth isn't the backwater village. Earth is the only lit-up metropolis in the galaxy, beaming radio into the dark, glowing at night so bright you'd see it from orbit. As far as we know, we're it. And 3IATLAS just sped past, didn't even tap the brakes. The flyby went down between October and December 2025, with the closest point around December 19th, about 1.8 astronomical units away. That's roughly 270 million kilometers, not exactly around the corner, but close enough for any probe to scoop up piles of data. From there, Earth is a pale blue dot, sure, but our atmosphere stands out in a spectroscope. Our civilization's radio chatter, the endless TV and phone signals, the radar we use to track satellites, it's all pouring into space, practically screaming, "Hey, something happening here." But 3IATLAS didn't care, or at least pretended not to. Its path never wobbled. Its speed held steady, only changing in ways you'd expect from sunlight or outgassing. It just kept heading for Jupiter, treating Earth like any other rock, just another Mars, just another Venus. Nothing special, nothing worth checking out. And that thought is actually a little scary. What if we're not the destination? What if we never were? What if something out there looked at our solar system, sized up everything from Mercury to Neptune, and decided Jupiter was the real prize? Before we get lost in what any of this means, before we start worrying about what it feels like to be ignored by the universe, let's nail down exactly what we saw. Let's get clear about the object itself, where it came from, what it looked like, and why astronomers everywhere scrambled the moment they realized what was cruising through our neighborhood. Because 3IATLAS isn't just another chunk of space debris. It's not some random comet making the rounds. This thing came from another star. That alone puts it in a category so rare, we've only ever confirmed 3 of them in all of human history. 3IATLAS is only the 3rd interstellar object we've ever seen passing through our solar system. The name tells you the essentials, at least if you speak a bit of astronomy. 3I is short for Third Interstellar Object. ATLAS is the name of the survey network that found it, Asteroid Terrestrial Impact Last Alert System, a set of telescopes built to scan the sky for anything that might crash into Earth. These telescopes operate out of Hawaii and Chile, and they work together, covering as much of the sky as possible, snapping images over and over to spot anything on the move. NASA helps fund the project. Naturally, they want a heads up if something dangerous is heading our way. On July 1st, 2025, someone spotted the object for the first time. It showed up as a faint, moving smudge against the stars. At a glance, it looked like just another comet, maybe a long-period one from the distant edge of the solar system, swinging in for one of those rare visits when sunlight wakes up all that distant ice, giving comets their bright, dramatic tails. So they logged the find, took some quick measurements, and then the real work started. Astronomers began crunching the numbers, calculating its path, feeding every bit of data into software that tracks gravity's pull and predicts where objects are headed. That's when things got interesting. The orbit wasn't a neat ellipse, one of those closed loops that keep planets, comets, and asteroids circling the sun again and again for eons. Instead, the path was hyperbolic. In plain terms, this thing was on an open-ended trajectory, moving way too fast for the sun to hold on to it. Objects on hyperbolic orbits don't stick around. They come in from the vastness between stars, swing past the sun, and then shoot right back out into interstellar space, never to return. These are one-time visitors. 3IATLAS was just passing through. It wasn't coming back ever, and it wasn't from around here. That realization set off a global scramble. Observatories all over the world, Chile, Spain, Hawaii, the US, and more, quickly turned their telescopes to track it. Hubble, still hanging in there, locked on. Even the James Webb Space Telescope joined in, collecting precious infrared data. Ground-based teams started coordinating, sharing observation schedules, and splitting up the work to make sure they didn't miss anything. This wasn't just another icy wanderer. This was a messenger from another star system, and suddenly everyone wanted answers. Where did it come from? Which star flung it out here? How many years or millennia has it been drifting through the void? What's it made of? Could its chemistry tell us anything new about how planets form around other stars? These questions fueled late nights at observatories, marathon data sessions, heated debates, and the kind of excitement that reminds scientists why they got into this business in the first place. Right now, 3IATLAS is still officially classified as a comet. NASA, the European Space Agency, all the big players, they've said it over and over. This thing looks like a natural wanderer, just ice and rock that formed somewhere else in the galaxy. It probably got kicked out of its original home by some wild gravitational dance, maybe a close call with a planet or another star, and then drifted through interstellar space for who knows how long before it randomly showed up in our solar system. When astronomers point their instruments at it, they see all the usual comet stuff: water vapor, carbon dioxide, carbon monoxide, dust. That's exactly what you'd expect. Comets are basically frozen leftovers from when planets were forming, and 3IATLAS fits right in. It's got a coma, a hazy, glowing cloud of gas and dust that wraps around the solid core. As the sun heats it up, the ice just skips the liquid phase and turns straight into gas, dragging dust along and building that fuzzy envelope. Sometimes that coma stretches out thousands or even millions of kilometers. People have watched 3IATLAS's coma, measured it, tracked its outgassing, jets of vapor shooting off when sunlight hits different spots. Those jets can nudge the comet a little, making small, unexpected changes in its path. Astronomers call those non-gravitational accelerations. Nothing weird about that, it's just physics doing its thing. By every normal test, 3IATLAS is a textbook comet. Its makeup, its behavior, how it looks, everything matches. There's no odd radio signal, no strange heat signature, no radar hinting at metal or anything artificial. All the evidence we've seen, all the data that's been released and checked by other scientists, points to a totally natural object. And yet something about its journey feels off. The way it approached Jupiter's gravitational zone, it's almost too precise, too clean to chalk up to pure luck. And when it flew past Earth, it acted like we weren't even here. The indifference is weird. It feels like something should matter but doesn't. Because if you chart its path, map where it's been and where it's going, run the numbers on its speed and timing, there's a pattern here that shouldn't exist in nature. 3IATLAS is heading straight for a spot near Jupiter called the Hill Radius, and it's aiming so perfectly. It's the kind of accuracy NASA and ESA spend years trying to nail with their own spacecraft. The Hill Radius isn't just a random line on a diagram. It's a real, physical region. Every planet has one. It's the zone where that planet's gravity wins out over everything else. Inside that bubble, you're mainly under the planet's pull. Step outside, and the sun or other planets start to take over. For Jupiter, the Hill Radius stretches out about 53 million kilometers. That's huge, roughly a third of the distance from the sun to Earth. Inside that sphere, Jupiter's gravity rules. That's where all its moons orbit, from the big Galilean moons Galileo spotted 4 centuries ago to the tiny oddballs we found recently. It's also where probes like Galileo, Juno, and soon the Europa Clipper head when they want stable orbits around Jupiter. You go there, you're in Jupiter's domain, no need to fight the sun's pull every second. So 3IATLAS, every test says comet, but its path, that's another story. Think of Jupiter's Hill radius like a cosmic harbor. On Earth, a harbor keeps ships safe from rough waves and strong currents, a place where you can drop anchor and not worry about drifting or burning fuel just to stay put. Jupiter's Hill radius does the same thing but with gravity. It's a patch of space where something, anything really, from a natural moon to an artificial probe, can hang out, steady and undisturbed without needing constant course corrections. Stick a satellite there, and Jupiter's gravity holds it in place, shielding it from the sun's pull and the nudges from other planets. If you want to study the outer solar system for years, this is where you want to be. Now here's the wild part. The intercept point for 3IATLAS, based on how it's moving right now, lands at about 53.4 million kilometers from Jupiter's center. The margin of error, about 60,000 kilometers either way. Take a second and let that sink in. That's not in the neighborhood of the Hill radius. That's not just close. That's landing on the bulls in a cosmic game of darts. To make it clearer, imagine standing in New York City and throwing a dart that hits the dead center of a dartboard in Los Angeles. Not just hitting California, not just touching the board somewhere. We're talking about nailing the center ring with less wiggle room than the size of the board itself. But even that's not quite enough to get across how tricky this is. When you throw a dart, you and the dartboard are both standing still. Here, nothing's still. 3IATLAS is tearing through space at tens of kilometers per second. Jupiter's racing around the sun at about 13 kilometers per second. The sun's blazing its own trail through the galaxy at hundreds of kilometers per second. Everything's moving, spinning, shifting. And somehow this object, probably drifting through interstellar space for millions or billions of years, arriving from who knows where, ends up lined up with Jupiter's Hill radius to within a tiny fraction of a percent. That just doesn't happen with natural comets. It can't. I want to be totally clear about this because details matter. Sure, space is full of stuff zooming around. Rocks, ice balls, you name it. There's a constant shuffle of things passing near planets. Gravitational close encounters happen all the time. Sometimes a comet or asteroid swings close enough to Jupiter or Saturn to get its path yanked around. Sometimes they just miss. But passing near a planet is a whole different ballgame from hitting a specific gravitational boundary on purpose, with an error margin measured in just tens of thousands of kilometers, even though you've traveled trillions of kilometers to get there. Just stack up the odds. First, this thing had to be kicked out of its home star system at exactly the right speed, an angle to even reach our solar system, which almost never happens. Most stuff ejected from other systems just floats through the void forever, never coming close to any other star. But this one didn't. By random chance, or maybe not, it pointed itself right at our sun. Then it had to sneak into our solar system at just the right angle. Too steep, and it rockets straight toward the sun or flies past everything without getting near a planet. Too shallow, and it barely brushes the edge of the system before slipping away, never meeting anything. The geometry has to be just so. First off, the timing here is almost uncanny. Jupiter takes 12 years to go around the sun. If 3IATLAS had shown up just a few years earlier or later, Jupiter would have been somewhere else entirely, and the whole approach would have been off. But no, the timing is spot on. This object reaches Jupiter's position right when Jupiter's actually there, like hitting a moving target blindfolded and still nailing it. Then there's the speed. If it's flying too fast, it just zips past Jupiter, doesn't even come close to the Hill radius, where Jupiter's gravity really grabs you. Too slow, and the sun's gravity can pull it in before it even gets to Jupiter, or the object just curls back toward the sun instead of hanging out in the outer solar system. But again, the speed is right. Everything just lines up. Now here, where things get even weirder, almost impossible to chalk up to random chance. 3IATLAS made its closest approach to the Sun, perihelion, back in late October 2025. That happened at about 1.4 astronomical units from the Sun. Just for context, 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So this thing actually got closer to the Sun than Mars ever does, but it didn't come inside Earth's orbit. Still, it got close enough that the sunlight should have been brutal, hot enough to make any surface ice boil off and turn straight into gas. Normally, comets get really unpredictable after perihelion. This isn't just theory, we've seen it over and over. That solar heat blasts off their icy surfaces, turning water ice, carbon dioxide, and carbon monoxide straight into gas. The gas escapes as jets, carrying dust out into space. But these jets don't shoot out evenly from everywhere. Comets are lumpy, weirdly shaped, and they tumble around. As they spin, different spots heat up, start blasting out gas, and then cool off again as they roll into shadow. The jets fire off in all sorts of directions, turning on and off as the comet rotates. All of this makes the comet's path unpredictable. The jets are like tiny, randomly firing thrusters, nudging the comet this way and that. Its path gets messy. Astronomers have to constantly recalculate where it's headed because gravity alone can't explain the motion. Some comets start to wobble, some speed up or slow down as they lose mass unevenly, and some even break apart when the stress or spin gets too intense. This kind of chaos after perihelion, that's just what comets do. But 3IATLAS didn't follow the script. Instead of its path getting messier and harder to pin down, the opposite happened. The trajectory actually tightened up. Its approach to Jupiter became more precise, almost like someone or something tweaked its course after it swung past the Sun. Telescopes all over Hawaii, Chile, the U.S., run by NASA, universities, and international teams all saw the same thing. The object's path became sharper, more dialed in. After perihelion, it was aimed at Jupiter's gravitational boundary even better than before. That's not how outgassing works. Random jets from sublimating ice don't make an object's path cleaner. They do the opposite. You get chaos, not precision. The way these gas jets fire off depends on whatever patch of ice happens to face the Sun, and that changes constantly as the object tumbles along. The jets vary in strength, direction, and timing. There's just no way random outgassing somehow makes a comet's trajectory more exact. If anything, it should make things sloppier, introducing more noise and uncertainty into the orbit. Still, 3IATLAS moves with this weird steadiness after perihelion. The way it approaches Jupiter's hill radius feels too precise for just random ice burning off. Either we're staring at cosmic luck so wild it's suspicious, or something, or someone, is steering it, making deliberate course changes right when it's closest to the Sun, and not by accident, completely hidden from our telescopes back on Earth because the Sun blocks our view. Then there's the Earth problem. We end up right back where we started, with this heavy silence and the cold shoulder that makes the whole thing feel off. The object passed pretty close to us on its way to Jupiter. Close enough that, if this thing was any kind of probe, and if it cared to study a technological civilization, you'd expect it to do something. Anything. Some kind of signal that we'd been noticed. Maybe a tiny nudge in its speed to get a better look at Earth's day side or night side. Maybe it would turn just a bit so cameras or sensors, whatever it's using, could face us instead of looking away. Maybe it would give off a quick burst of heat, the kind you'd see if instruments powered up to collect data during this rare flyby. Maybe we'd pick up a weird radio echo, a hint that something electronic was switched on. But no. None of that happened. No brakes. No speed up, no spin we could spot in the light curves. No odd heat signatures in the infrared. No radar ping that hints at metal or machinery. No radio blip. Nothing. The object just passed us by, totally uninterested, like we're just another chunk of rock orbiting a forgettable yellow star. Like a car on the highway that doesn't even slow down at your exit, doesn't signal, doesn't glance at the signs, just keeps driving. That total indifference. It's actually more unsettling than if it had acted hostile. Hostility would mean we matter. It would mean we're a threat, or at least worth acknowledging that we're players in whatever's happening out there. Indifference means we're not even in the game. We're just background noise, maybe a data point for someone's survey, but not interesting enough for a closer look. We're not the goal. We're just a pit stop on the way to something that actually matters. So think about what that says strategically. If you're some intelligence out there watching the solar system, sizing things up, what do you care about? If you've got the tech to send probes between stars, what's your priority? Biology, intelligence, technology. Those are guesses humans make. We assume the big prize is finding someone like us, that any visitor would be drawn straight to the one planet broadcasting radio static and lighting up the night. We assume we matter. But what if intelligence isn't the big deal we think it is? Maybe technology, at least at our current stage, just isn't that interesting. Maybe life is so common in the galaxy that a planet bubbling with biology doesn't even get a second look. Maybe the real gold in a star system is somewhere else entirely. Take Jupiter, this giant ball of gas, no solid ground, no way to support life as we know it. What if it's actually way more valuable than Earth? Jupiter brings a lot to the table, stuff Earth can't even dream of. If you're planning for the long haul, if you want infrastructure that lasts centuries or even millennia, Jupiter starts to make sense. Need power? Jupiter's got it. Not just a little, an insane, endless amount. We're talking about energy on a scale that makes every human project look like lighting a match in a hurricane. Jupiter has the biggest, baddest magnetic field in the solar system. Its magnetosphere stretches millions of kilometers out. If we could see it, Jupiter would look like this massive glowing bubble, way bigger than the planet itself, buzzing with trapped, supercharged particles. Electrons and ions whip around at wild speeds, some close to the speed of light. The radiation belts crank out energy that just dwarfs anything we've managed to build. This isn't some physics experiment in a lab. This is nature, turned up to 11, with real, measurable energy just waiting for anyone with the right gear to scoop it up. Any civilization that's figured out how to harvest electromagnetic energy, honestly, if you can build interstellar probes, you've probably nailed that part, would see Jupiter as a cosmic battery. The magnetosphere never stops generating power. It runs off Jupiter's own spin, its monster magnetic field, and the solar wind blowing in from the sun. As long as Jupiter's around, the energy keeps coming. You could keep fleets of autonomous probes running forever just by tapping into that natural power. Forget hauling fuel. Forget solar panels that break down or reactors that conk out after a decade or two. Just park in the right spot and collect energy nonstop. For us, getting close to Jupiter is dangerous. The radiation would fry our electronics, so we load our spacecraft with shielding. Galileo, which orbited Jupiter from 1995 to 2003, was built tough and still took a beating over time. Juno's out there now, but it swoops in and then swings out to safer spots, dodging the worst of it. The upcoming Europa Clipper will do the same, quick flybys, then retreat to regroup. To us, Jupiter's radiation is a threat, but flip the perspective. For a civilization with different tech, maybe tougher materials, smarter engineering, that radiation isn't a problem, it's a gold mine. No need to mine asteroids for uranium, no sprawling solar farms to patch up every decade. The power is just there, always renewing itself, handed over by the laws of physics. If you know how to capture it, Jupiter isn't just valuable, it's the best energy source in the solar system. Now, orbital stability sounds like one of those dry, technical topics you skip right past, until you realize what it really means for anything you want to keep running out there for the long haul. Take the Hill radius. It's not just some invisible line in space, not just a trivia fact for astronomers. It's basically cosmic parking. Inside that zone, you can leave a satellite or a probe and trust that it'll stick around without constantly burning fuel or fighting to stay put against the gravitational tugs from other planets or the sun. We're not talking days or weeks, either. Try centuries, even thousands of years, and you barely have to lift a finger for station keeping. That opens up a whole world of possibilities. If you don't have to haul tons of extra fuel or build complicated systems for endless maneuvering, suddenly your hardware can be lighter, cheaper, and way less likely to break down. Gravity does the heavy lifting. You put your instruments where you want them and physics keeps them there. For any mission that needs to watch a star system for years on end, collecting data, sending reports, maybe just quietly listening in, this is prime territory. You're not fighting the universe, you're using it. Set up shop where the natural orbits and resonances work in your favor. That's just smart design. And then there are the Lagrange points, those special spots where gravity balances out and creates natural rest stops in space. Jupiter's Hill radius has some of these built right in. The L1 and L2 points stand out. L1 sits between Jupiter and the Sun, about 50 million kilometers from Jupiter's center. Park something there, and the tug from the Sun and Jupiter cancel each other out. It barely takes any energy to keep your spot. L2 is on the far side of Jupiter from the Sun, same distance out. Anything sitting at L2 stays tucked in Jupiter's shadow, practically invisible to any telescope looking from inside the solar system. These aren't just theoretical. They're real places, actual chunks of space where physics gives you a free pass to set up long-term shop. Earth has its own Lagrange points with the Sun, and we've already planted spacecraft there. Look at the James Webb Space Telescope, quietly parked at Earth-Sun L2, soaking up the view. If we can do that with our current tech, just imagine what a civilization with interstellar reach could pull off at Jupiter's L1 and L2. But Jupiter's Hill radius has another ace up its sleeve: location, perspective, the view. From Jupiter's orbit, about 5 times farther out from the Sun than Earth, you get this sweeping panorama of the inner solar system. Every rocky world, Mercury, Venus, Earth, Mars, laid out before you. Every place where interesting chemistry or even life might be happening, all right there, usually in clear view with almost nothing blocking your line of sight. And let's not forget about radio waves. Earth is constantly leaking radio signals, TV, radio, cell towers, satellites, the whole mess, out into space. All that electromagnetic noise races outward at light speed. By the time it washes over Jupiter, the signals are faint, sure, because distance eats away at strength. But faint isn't the same as silent. With good enough equipment and enough time, you can dig those whispers out of the cosmic background. From Jupiter, you could tune in and catch pretty much everything Earth civilization beams out, like having a front row seat to the planet's electromagnetic buzz. It's not just Earth we're talking about. People are already sending missions to Mars, humans, rovers, orbiters, the whole works. Those machines beam loads of data back home, and anyone with the right tools could pick up those signals too. Over on Venus, we have orbiters studying the planet's brutal atmosphere and weird geology. Mercury, Bepi Colombo's circling it right now. There's a flurry of activity all across the inner solar system. If you sat out by Jupiter and watched, you'd see all this evidence of a civilization stretching its legs, getting bolder, pushing out past its home planet. You'd spot the launches. You'd notice when a new cluster of satellites pops up. If you paid close attention, you could even track how our technology's evolving just by watching the way our radio chatter changes year by year. It's kind of like anthropologists watching a new society form, taking notes, gathering data, piecing together the story as it happens. Now picture yourself in Jupiter's neighborhood. It's a nightmare out there, radiation everywhere. The kind of place that shreds electronics and cooks anything alive. Human spacecraft need absurd levels of shielding just to survive for a while. But that same radiation, all those high-energy particles, they're actually useful if you want to stay hidden. The magnetosphere acts like a natural bunker, blasting interference in every direction. Radio waves scatter and disappear in the plasma soup. Good luck trying to see anything with a telescope. The auroras and background noise drown out faint signals. If you wanted to keep your technology secret from Earth's prying eyes, if you wanted to run operations without anyone noticing unless they knew exactly where to look, Jupiter's radiation belts are basically perfect. You could stash a whole fleet of probes out there, dozens or even hundreds, spread across all that empty space. And honestly, Anyone on Earth trying to spot them would be out of luck. There's just too much noise, too much static, and way too much ground to cover. Even if someone caught a whiff of something unusual, tracking it down would be nearly impossible. This isn't just some wild idea. It actually makes sense from an engineering and strategic standpoint. And that leads to a weird, maybe even unsettling thought. 3IATLAS might not care about us at all. Earth could just be one more blip in the background. The real goal could be about long-term infrastructure, setting up shop somewhere with energy, stability, great positioning, and the kind of cover you just can't get anywhere else. Imagine you're the one sending something out here. You want eyes and ears in a new star system. You want to know what's going on, what resources are up for grabs, whether anything interesting pops up in the next 1,000, 10,000, or even 1,000,000 years. Maybe you need a relay, a way to talk to other probes, pass messages back across the stars. You want a base that runs on its own, fixes itself as much as possible, and doesn't need someone at home to babysit it. That's the kind of thinking that puts you out by Jupiter, quietly watching, while the rest of us are busy making noise closer to the sun. So where do you put it? Not on Earth. Honestly, Earth is a terrible spot. Sure, there's a technological civilization down here, but that just complicates things. Civilizations are messy. They change, they grow, and sooner or later, they start looking up and noticing stuff in their skis. If you park some observation gear near Earth and humans eventually catch on, well, now you've got a first contact mess on your hands. You've blown your cover. Suddenly, you're the center of attention and you have to deal with whatever reaction the locals throw at you. You're tangled up in their story whether you like it or not. But Jupiter's basically perfect. It's huge, pumping out energy. Gravitationally, it's steady. You get a great vantage point for watching the inner solar system. Plus, the radiation out there makes it really hard to spot anything you've parked nearby. And best of all, nobody's home. No life to accidentally mess with. No civilization poking around. Nothing likely to stumble across your setup. Just you, the physics, and streams of data pouring in from the real action closer to the sun. Earth. It's just another blip, no more special than the asteroid belt with all its wild dynamics, no more interesting than Titan and its weird lakes, not even more important than Mars, which might have had life before and could maybe host it again if humans ever get their act together. So what are we really? We're data points. Just catalog entries in whatever grand survey is running out there. Maybe we're interesting enough that someone's logging our radio chatter. Maybe our progress gets a few notes scribbled down, but we're not worth a direct visit. Not now, maybe not ever. We're the locals, and if there's a visitor out there, it's not looking to invade or trade or even say hello. It's just here to build something, some infrastructure for reasons we can't begin to imagine, working on timescales that make all of human history look like a blink. But humans love their invasion stories. Fleets of ships swooping in to strip our resources, enslave us, or wipe us out. That's the stuff of movies and late-night worries. We get it. Conflict, competition, the fear that someone wants what we have. All those stories rely on the idea that we actually matter, that we're valuable enough for someone to cross the stars just to mess with us. But if you look at the reality hinted at by 3IATLAS's path, it gets darker and honestly a lot more unsettling. We might not matter at all. Maybe Earth is just one more rock in the habitable zone. Our civilization, just another line in an endless database, another case of carbon-based life inventing technology. Nothing unique, nothing special. Everything we care about, everything we've built, might just be background noise collected by the observation grid because, well, that's what it does, not because we're important. We're the locals, not the destination. Jupiter's the destination. And realizing that, really letting it sink in, seeing ourselves as background instead of center stage, that might be the real lesson here. And yeah, it stings. Think about it. Maybe we're watching the rollout of something that's been in the works longer than humanity has even existed. Interstellar travel isn't just hard. It's almost ridiculous when you look at the timescales involved. Even if you've got technology way ahead of ours, even if you're sending out unmanned probes, you're still dealing with distances that make human history look tiny. Stars aren't just far, they're light years apart. Light itself, zipping along at 300,000 kilometers per second, takes years just to get to the next star over. Alpha Centauri, our closest neighbor, sits about 4.4 light-years away. Say you could go at 10% the speed of light, wildly advanced by our standards. You're still looking at a 44-year trip, and that's just to the nearest one. Around here, stars are scattered several light-years apart. If you're trying to explore them in any methodical way, you're signing up for missions that run decades, maybe centuries, even thousands of years. You launch a probe and you'll never see what comes back. Your kids won't either. The whole civilization that sent it might not even be around anymore by the time you get a ping. This is patience on a level that's almost impossible to grasp, geological, astronomical patience. So if something or someone actually launched 3IATLAS, if this wasn't just some cosmic accident, they did it knowing the mission would stretch out over timescales that make our lifetimes look like blinks. This isn't about quick scouting or sending back real-time updates for next steps. The whole thing is built on sending something into the galaxy and letting it run for centuries or longer, smart enough to make its own decisions, aiming for goals that might outlive the beings who set them in the first place. And maybe this object isn't just a probe. Maybe it's more like a carrier, a mothership, built to haul a bunch of smaller probes and drop them off when it gets to its destination. Sounds like science fiction, but actually, researchers have seriously considered it. They call it Sentinel theory, or sometimes the von Neumann probe idea. Basically, they crunch the numbers and look at the physics, and this kind of setup just makes more sense. Think about the alternative. If you want to explore the galaxy, you could send one probe to every star system. But that's crazy inefficient. Every probe needs its own engines, power, sensors, communications, the whole bundle. Do that thousands of times and now you're paying the price in mass and energy, and even super advanced civilizations probably have budgets. But what if you send out big carriers instead? Each one is built for the long haul, tough enough for interstellar travel, loaded with strong engines, thick shielding, and power systems that last. You don't pack every instrument into the carrier. Instead, you fill it with small, specialized probes. Once it arrives, those little guys handle the local exploration, each with just enough gear to do the job and stay in touch. That way, you only pay the big price once, not 1,000 times over. The carrier draws closer to the target star system, slowing down, a process that eats up just as much energy as speeding up did on the way in. It aims for a spot where gravity settles things down, maybe near a gas giant's hill radius, a kind of cosmic parking space that doesn't need a lot of fuss to stay put. Then comes the big moment, the dispersion event. The payload bay yawns open. Dozens of smaller, autonomous units peel away from the carrier, each loaded with its own destination and mission instructions. They split off, nudging their courses with tiny bursts from their thrusters, spreading out across the star system. Some of these units head for Lagrange points, those gravitational sweet spots where you can just sit forever if you want. Others aim for orbits around big planets or moons that look interesting. A few dive into the inner system, on a mission to check out rocky planets sitting in the habitable zone. Each unit picks its spot, and together they form a web of observation posts that cover the entire system. They watch, they listen, they scoop up data, electromagnetic noise, spectral readings, anything that moves or changes out there. They run on their own, making decisions based on what they're programmed to do, sometimes tweaking their behavior if they spot something unusual. And then they send what they've found. Not all the time. The power demands for interstellar chatter are brutal. But when the battery, up, the memory's full, or something big happens, they fire off bursts of data. Sometimes they send it back to the carrier if it's still around. Sometimes to another probe passing through. Sometimes straight across the stars, a tight, compressed pulse carrying everything they've learned over years or decades. The beauty of this setup is how efficient it is. You don't have to build every probe tough enough for a long-haul journey. The expensive stuff, the engines, the shielding, the gear for crossing light years, stays in the carrier. The little units can be cheap, simple and easy to make in bulk. One carrier can drop dozens, maybe hundreds of these observation units in a single go. Do that mission after mission, system after system, and you end up blanketing the galaxy in a way that sending single probes just can't match. And here, where things get wild, picture a civilization running this playbook for millions of years. They could fill the galaxy with networks of sentinels. Every star system visited gets its own grid, running on autopilot, gathering and reporting back, no hand-holding from home required. The original civilization might vanish, war, collapse, entropy, take your pick, but the networks would keep working. The probes would still be out there, still watching, still collecting data. The whole setup would become part of the galaxy itself, outlasting the folks who built it. If 3IATLAS is part of this kind of operation, if what we're seeing is a carrier making its approach and setting up for deployment, then this isn't first contact. We're not seeing diplomats or explorers looking to chat. We're watching infrastructure go in. The solar system is getting colonized, not for homes or resources, but as a foothold for observation and strategy. And it's happening whether we want it or not, ready or not, even if we never notice. That makes the timing of the Earth flyby pretty hard to ignore. If this was just a random comet, you wouldn't expect it to pass by when Earth's night side, our cities and satellites blazing, faced directly toward its path. But that's what happened, right when our technology stood out the most, glowing against the dark side of the planet. All those radio signals we constantly send out, TV shows, FM radio, radar pings from satellites, cell phone chatter, they just leak into space nonstop. For about 100 years now, ever since Marconi and his crew figured out radio, this noise has been bubbling outward from Earth, getting bigger every second. Right now, it stretches almost 100 light years in every direction. Anything out there with a sensitive enough antenna would catch us, plain as day. They'd know there's something alive and noisy orbiting the sun, making all kinds of unnatural electromagnetic patterns, proof of intelligence, or at least technology. So when 3IATLAS swung by, it flew right through our signal cloud. If it had any kind of receiver or antenna, anything at all for picking up M waves, it would have scooped up a century's worth of our broadcasts. News, sitcoms, pop songs, encrypted messages, the nuts and bolts of our whole technological society, laid out in radio waves free for the taking. But nothing happened. No sign it even noticed us. No reply, no flicker, not even a flicker of curiosity. If it logged our existence at all, it filed us away as background noise. Maybe just something to transmit home, maybe not even worth that. Honestly, from a scouting perspective, that tracks. If Earth isn't the main target, you don't stop here. If you're on a survey mission, checking off planets and stars, you log the interesting stuff, but you don't get distracted. Sure, Earth is weird, probably not too many places like it, even if we're not the only ones. But interesting doesn't mean important. It doesn't mean you pull over for a closer look. If the real job is to set up shop somewhere safe, somewhere you can watch the whole solar system, you skip the detour and head straight for the best vantage point. It's kind of like driving cross-country. You don't pull off the highway for every little town just because it's there. You see the signs. You take note. Maybe you slow down a bit if something really catches your eye, but unless you have a reason, you keep going. 3IATLAS did exactly that with Earth. No slowing down, no circling, just a straight shot past us onto Jupiter. That's where it's headed. That's the place that matters, whatever its goal is. And that's the point, isn't it? The object's actions couldn't be clearer. We're not the reason it came. We're not special, just another yellow star with some rocks around it, another system to tick off on the list. Not worth burning extra fuel or time. And that's kind of a gut punch, isn't it? We like to think we matter, that any visitor would be drawn straight to us, eager to make contact. But apparently that's not how it works. This is where things start to get uncomfortable, where guesswork and evidence start to blur together. If Jupiter is the real target and if this thing plans to set up a base or observation post, then what comes next? What would we actually notice? Or, maybe more to the point, what would we miss if this is really happening over the next few months? Researchers who model interstellar probes have a pretty clear idea of what we'd see. As 3IATLAS nears Jupiter's Hill radius, basically the edge where Jupiter's gravity wins out, our instruments might catch what looks like a breakup event. Not some big dramatic explosion, nothing obviously artificial. Just the main object quietly splitting into smaller pieces. The way comets sometimes fall apart under gravity looks natural, but if you're paying attention, it's anything but ordinary. Natural comets break apart near big planets like Jupiter all the time. It's not rare, there are plenty of records. When a comet swings close, tidal forces, gravity pulling harder on one side than the other, can rip it to pieces if the comet isn't tightly held together. Shoemaker-Levy 9 did just that in 1992. It split into more than 20 fragments, which slammed into Jupiter's atmosphere in 1994. Telescopes everywhere caught the show. We learned a ton about what comets are made of and about Jupiter itself. Honestly, fragmentation near Jupiter is so normal that nobody gets too worked up when it happens. That's just how things go for comets. But what if the breakup doesn't look random? Instead of the usual chaotic spray, imagine the fragments start acting like they're on a mission. Maybe they split off along neat lines. Maybe each piece slows down or speeds up on its own, tweaking its path in ways that just shouldn't happen without some kind of engine or guidance. Some of these fragments might head straight for Jupiter's L1 Lagrange point, the kind of cosmic sweet spot between Jupiter and the Sun. Others peel off toward L2, the stable zone on the far side. A few might steer deeper into the Jovian system, passing close to the big moons. Io, always rumbling with volcanic eruptions. Europa, hiding that mysterious ocean under its ice. Ganymede, showing off its own magnetic field. Callisto, pockmarked and ancient. Each fragment settles in somewhere that actually makes sense if you wanted a good view or special data. It's almost like they're picking the best spots for surveillance. The weird part, these objects are pretty small. Right now, estimates for 3IATLAS's nucleus range from a few hundred meters up to 5 kilometers, but it's tough to be sure because a comet's coma hides everything. If it splits, each fragment could shrink down to tens of meters, maybe even smaller. That's nothing in astronomical terms. From Earth, even with the sharpest telescopes, you'd be hard-pressed to spot something that size, unless you knew exactly where to look and had gear dialed in perfectly. Now add another headache. Many comets and asteroids are coated in dark stuff that barely reflects sunlight. Low albedo means they're practically invisible, and Jupiter's radiation messes with radio signals and creates a storm of background noise. Even if someone got suspicious and started searching for tiny fragments drifting away, finding them would be a nightmare with the tools we have. Within days or weeks, those fragments could spread out across the entire Hill sphere, the region where Jupiter's gravity calls the shots. Each one finds a stable pocket, an orbit or a Lagrange point and just parks there, barely needing any fuel to hold its spot. From those vantage points, the real work starts. They watch, they listen. They scoop up data about everything in the inner solar system, Earth's radio chatter, satellite launches, new tech, Mars missions, asteroid traffic, the solar wind, the magnetic fields, and 1,000 other details that could matter for understanding how this star system ticks, and what the future might hold here from planeta to come. They transmit, but not all the time. Sending signals burns through power, and cross-system or interstellar communication eats up even more. So they wait. Maybe they only send when something interesting happens, or when they have enough data to make the effort worthwhile, or maybe they just stick to a schedule set ages ago. When it's time, they fire off bursts of information. Sometimes the message goes to a relay station parked at another Lagrange point. Sometimes it shoots straight to receivers in other star systems. Sometimes they just hand it off to the next carrier passing by, like a baton in a relay race. From Earth, from where astronomers track 3IATLAS, we just see a comet breaking up near Jupiter. That's not rare. It fits right in with natural processes, no reason to sound the alarm. What we wouldn't see is the network quietly taking shape right in front of us. Dozens, maybe hundreds of autonomous probes slipping into stable spots around the solar system, nestled deep within the Hill radius or even farther out. each probe settling in for a mission that could outlast all of human civilization. They'd be too tiny to spot, too dark, too well camouflaged in the background noise. By the time anyone guessed that something odd was going on, the network would already be up and running, and there'd be no way to confirm what really happened. No proof that anything artificial took place instead of a regular comet fragmenting. No way to tell the difference between random chunks of rock tumbling through space and cleverly placed observation platforms quietly doing their job. The uncertainty would be total. Some scientists would stick to the natural explanation, pointing at past events. Shoemaker-Levy 9, other comets, saying, "Look, this happens, we know how it works, no need for wild theories." But others would raise their eyebrows at the trajectory, the sharp adjustments after perihelion, the suspicious timing of the breakup right at the hill radius, and say, "You really think that's just chance?" The arguments would fly. Journals would fill up with papers from both camps. Conferences would get heated. The public would watch from the sidelines, baffled and maybe a little scared, as experts clashed over whether we'd just seen alien tech arrive in our solar system. News coverage would swing wildly. One minute, alien probe confirmed. The next, calm down, nothing happened. But no one would have conclusive proof. No one could say for sure what actually went down. And in that fog of uncertainty, if the network really existed, it would just keep working totally undisturbed. This is speculation. I want to be crystal clear about that. There's no hard evidence that any of this is happening or ever will, but the pieces are all there. The trajectory is real, we can measure it. The approach to Jupiter's hill radius is precise and on record. Jupiter's value as an observation post is obvious. Physics and orbital mechanics back that up. The object ignored Earth during its flyby, and we know that for a fact. These are data points, independent of whatever story we tell ourselves. So, what do those facts actually mean? Are we watching a random comet, a chunk of ice and rock tossed from another star, just happening by some freakish luck to approach Jupiter's gravitational boundary with spacecraft-level accuracy? Or are we witnessing a plan, a mission set in motion millions of years ago, long before humans, before Earth had civilization or technology or any of the things we think make us unique, a plan now reaching its final act? NASA and other space agencies keep saying, over and over, that 3IATLAS is just a regular interstellar comet. Nothing artificial, nothing strange. They've got the data to back it up. Spectroscopic readings show water vapor, carbon dioxide, carbon monoxide, and dust. There's a coma, the classic hazy cloud of gas and dust that shows up when comets heat up near the sun. Scientists have seen jets of vapor bursting from its surface, creating little nudges that match the changes in its path. All of that comes from real observations. Based on what we know and the physics we trust, the scientific community calls it natural. But science is only as good as its tools and its theories. Consensus covers what we can actually measure, what our models can handle, and what fits the rules we've built after years of studying comets and asteroids. It doesn't cover what we're missing. It doesn't cover the blind spots in our instruments. It doesn't rule out the chance that something could be built to look exactly like a comet, so perfectly that, unless you get up close and personal, you never know the difference. Think about it from the other side for a second. Imagine you're designing an interstellar probe and you want to keep a low profile. You don't want to set off any alarms or get noticed by some curious, tech-savvy civilization. Attention brings questions, and questions bring trouble. So, how do you hide in plain sight? How do you build a probe that slips by without raising eyebrows? Easy. You make it look like a comet. You give it a coma just like sublimating ice would make. You make sure its spectroscopic fingerprint matches what any astronomer expects to see: water, carbon dioxide, and all those other icy ingredients. If you need to tweak your course, you wait until you're at perihelion, when you're closest to the sun and hidden from prying eyes on the most advanced planet. Use the sun as your cover. Make your moves when no one can watch. If your probe needs a propulsion system, you design it so the exhaust looks like normal comet outgassing. Maybe you even use the real thing, heat up some ice, create jets, and steer with those. To anyone watching from afar, it just looks like natural behavior. The spectral lines match. The appearance is spot on. The physics is identical. The only thing different is the motivation, the steering, the purpose. And those are the details that are nearly impossible to spot from a distance. You blend in, just another object drifting through the solar system until it doesn't matter anymore, until you've reached your goal or started your mission. By the time anyone gets suspicious or starts asking questions, it's too late. You're already there. The infrastructure is running. The observation network is up. Whether anyone believes it or not or can prove anything doesn't matter. You've done what you came to do. This isn't about wild theories or paranoid daydreams. It's not about seeing connections where there aren't any. This is about facing what the data tells us, especially when it doesn't line up with the story we'd like to believe. Nature doesn't do perfect precision very often. So when you see something hit a target with almost impossible accuracy, you don't just shrug it off. You dig in. You ask why. You wonder what else could be going on, even if the answer isn't comfortable, even if it upsets everything you thought you knew. Here's the thing, we don't like feeling small. We're raised to believe we matter. We write ourselves into the starring role. If something or someone from another star system shows up, we can't help but assume they're here for us. Maybe to study us, maybe to help, maybe to threaten, but always with us at the center. After all, we split the atom. We walked on the moon. We built telescopes that reach into deep space. Surely all that effort and curiosity makes us special enough for someone else to notice. But the universe doesn't care what we think we deserve. It doesn't play favorites. 3IATLAS, with its laser-straight shot toward Jupiter and total disregard for Earth, might just be trying to teach us that. Maybe we're not the main event. Maybe we're not even all that interesting. For all we know, civilizations like ours pop up all over the galaxy. We're just another dot on the map. Maybe to someone out there, we're just another data point, just another item in a catalog. Maybe we're background noise in a much bigger survey. Sure, they might log our radio signals, they might notice our satellites, but that doesn't mean we're worth a detour. It doesn't mean anyone's coming all this way to meet us. We're not the prize, we're just part of the scenery. And realizing that, truly feeling it, might be the real lesson of 3IATLAS. Not what it tells us about comets or alien solar systems or planetary formation. The real gift is the uncomfortable truth that we're probably not as important as we hope. It's a mirror reflecting back all our assumptions about how much we matter. History's full of moments when we got this wrong. We thought the universe revolved around us, literally. Then Copernicus, Kepler, and Galileo proved we were just another planet circling the sun. We thought our sun was unique, maybe the only star. Then we found billions more in our own galaxy. We thought our galaxy was the whole universe until astronomers like Hubble showed us there are countless others. Every time we've tried to make ourselves the center, reality's pushed us off that pedestal. We're not at the center of the solar system. Our star isn't special. Our galaxy is just one among billions. Each time it stings. Each time it shrinks our sense of importance. But each time it also frees us. It lets us see the universe as it really is, not as we wish it to be. Maybe this is just another one of those reality checks. 3IATLAS might be showing us that we're not even listed on the cosmic map, not because anyone's dodging us, but because we're simply not relevant to whatever's happening out there. We're background noise, scenery, just some data points in surveys that aren't really about us. Maybe it's time to get comfortable with that, to see ourselves as a side note instead of the main story. That might be the mindset we need for whatever's coming next. One thing's obvious, no matter how this 3IATLAS thing plays out. The old idea that we're alone out here, that we've got all the time in the world to grow up before bumping into anything else, that's out the window. Even if this object turns out to be completely natural, even if every weird thing about it gets a boring explanation, we still have to face the facts. Interstellar objects are drifting through our solar system. They're coming from other stars. They're carrying clues about places in the galaxy we'll never reach with the tech we have. They're proof that the space between stars isn't as empty as we thought, that there's actual traffic out there, and we're only just starting to notice. We're not isolated. We're not tucked away in some quiet patch of the galaxy where nothing happens. We live in a region that's part of a much bigger flow. Other stars throw stuff our way. Other forces and maybe even other civilizations are sending things through our neighborhood. Only now are we waking up to the idea that our quiet corner might be more crowded than we imagined, that things are happening all around us that we barely understand, and that all this activity could have been going on long before humans showed up. And if some of that activity isn't natural, if some of these objects are probes or infrastructure or pieces of some network put in place by intelligences we've never met, then we're not alone, and not in some distant, abstract sense. We're talking about a much more immediate kind of company than radio telescopes ever hinted at. Someone's watching. Someone's keeping records. Our solar system might already be in use for purposes we can't even guess at by beings who haven't introduced themselves, and maybe never will, because we're just not important enough to bother with. Trying to figure out what's really happening here is a massive challenge. Spotting tiny objects way out in space pushes our technology to its limits. Our best telescopes, whether on the ground or in orbit, are built to study galaxies billions of light years away, not to track faint, fast-moving things zipping around our own solar system. The tools and skills you need are different. The problems are different. Honestly, most of the time the money and attention go to deep space astronomy, not to keeping an eye on what's close by. So we're not always looking where we should, when we should, or with the right gear. Ground-based telescopes have to deal with the atmosphere. Even at the best spots, high up in Chile or Hawaii, where the air is thin and the sky is dark, atmospheric turbulence blurs the view, water vapor blocks some wavelengths, and you can only observe when it's actually night and the sky's clear. Adaptive optics can help, tweaking mirrors hundreds of times a second to sharpen the image, but there's only so much you can fix. Space telescopes skip the atmosphere, but they've got their own limits. Hubble, still going strong after more than 30 years, can't whip around to new targets quickly. It needs time to aim, lock on, and stabilize before it can start collecting data. The James Webb Space Telescope, our most powerful infrared eye, is even more restricted in some ways. Its spot out at L2 gives it a narrow view, and while it can see incredibly faint things in stunning detail, you have to know exactly where to point it. It's not built for wide sweeps of the sky, hopping to stumble across something unexpected. The real challenge is figuring out where to look. Space is just enormous. If you think about the area out to Jupiter, the sheer volume around the sun is mind-boggling. Even if you had telescopes that could spot every pebble, there's no way to watch all that space at once. So you have to pick your battles. You aim your telescopes at certain spots, chase down specific leads, and decide where to spend your time and money. But those decisions don't always match up with hunting for interstellar visitors or catching something odd happening near Jupiter. Take 3IATLAS, for example. We spotted it only because it passed through a patch of sky Atlas was scanning for near-Earth asteroids. If it had come in from a different angle or at a different time, we probably would have missed it. We found it thanks to luck, right telescope, right patch of sky, right moment. So how many have slipped by? How many interstellar objects have zoomed through the solar system, too faint, too quick, too far out of the usual plane, or just in the wrong place at the wrong time for anyone to notice? Nobody agrees on the exact numbers, but some scientists think we're only catching a small slice of what's actually out there. Maybe 10%, maybe less. The rest are just out there now, drifting between the planets, following paths we'll never track, holding secrets we'll never get to study. We're working with scraps, trying to figure out a whole story from just a handful of lucky finds. That's what makes interpretation so tricky. With only a few examples, and each one its own brand of weird, it's tough to spot trends or say what's normal. So far, we've confirmed just 3 interstellar visitors, Oumuamua, 2I/Borisov, and 3IATLAS. That's nowhere near enough to build a solid statistical picture. Are these the rule or the exceptions? Are we seeing the ordinary or just the oddballs that happened to cross our path while the rest slipped by unnoticed? And even when we do get a close look, things stay murky. Remember Oumuamua? When it showed up in 2017, it did things we didn't expect, like speeding up in a way we couldn't chalk up to normal comet behavior. No tail, no visible outgassing, just weird acceleration. People tossed out all sorts of ideas. Maybe it was a block of hydrogen ice, maybe nitrogen, maybe even a solar sail built by someone else. Every theory had holes, and by the time we started asking the right questions, Oumuamua was already heading out of the solar system, too far for a closer look. We're still arguing about what Oumuamua actually was. Some scientists say it was just an oddball comet or asteroid, nothing artificial at all. Others think the weirdness is too much to ignore and that we should at least keep our minds open to stranger possibilities. The truth is, the data just isn't enough to settle it. We moved fast to gather what we could, but it wasn't enough to close the case. Now, 3IATLAS brings similar headaches. The trajectory is weirdly precise, a long shot for a natural object, but not impossible if you believe in coincidence. The way its path changed after perihelion is unusual, though you can imagine some natural explanations, like outgassing pushing it just right. Its apparent lack of interest in Earth might be meaningless, or maybe it's the whole story, depending on how much intentionality you're willing to see in its movement. We're basically in the same spot with 3IATLAS as we were with Oumuamua. The data just isn't clear-cut. You can look at the numbers, the trajectories, the weirdness, and depending on your perspective, you end up with totally different stories. One person sees a fluke of nature, someone else sees something intentional. And since we can't fly out there and take a close look, no spacecraft, no up-close investigation, we're just stuck. All we have are arguments and guesses, with no real way to put the debate to rest. Honestly, maybe that's the whole point, if something or someone is actually putting these things out there. If you want to build infrastructure in another star system without getting noticed by the locals, you don't make a big show of it. You keep things subtle, quiet. You act in ways that could pass for natural. Let the locals argue among themselves. Let them second-guess every data point while you quietly get your work done. By the time anyone agrees on what happened, you're long gone and whatever you came to do is already up and running. Whether the locals even believe your project exists doesn't matter. The mission's finished, the network's working, and no one's the wiser. From a strategic angle, you can see why this works. If you're thinking in terms of centuries or even millennia, you don't need approval, you don't need anyone's help. You just need them to stay out of your way. The easiest way to make sure they don't interfere, don't give them a clear reason to panic. If everything's ambiguous, if even the experts can't agree on what's going on, nobody's ready to take action. Uncertainty makes people freeze. If no one can agree on what you're doing, or even if you're really there, then no one can mount a serious response. So here we are, left watching these odd visitors to our solar system, trying to make sense of it all with only scraps of evidence. We see orbits that look too precise. We spot behaviors that don't fit what we expect. Sometimes it looks like there's a pattern. Maybe there is, maybe it's just our brains connecting dots that aren't really connected. In the end, we each have to decide what story we believe. Science tells us to play it safe. Stick to natural explanations. Demand strong evidence before believing the wild stuff. Don't get carried away. That's how science moves forward without chasing every shiny new theory. But good science also means following the facts, even when they lead somewhere uncomfortable. If the evidence doesn't fit our old ideas, we're supposed to be ready to update those ideas, even if it means considering something we never expected. That push and pull is tough. Stay skeptical, but don't shut your mind. Demand proof, but don't ignore the weird stuff. Assume it's natural, but don't twist yourself in knots to make the natural explanation fit when it just doesn't. It's a hard line to walk, especially when the answer could really matter, not just for scientists, but for all of us. And if we get it wrong, if 3IATLAS turns out to be perfectly natural and we've convinced ourselves it might be artificial, we've wasted time and energy chasing shadows. We've confused the public, maybe even scared people for no good reason. Worse, we risk our own credibility. The next time there's a real concern, people might not listen, and that costs us more than just a bit of pride. If we're onto something here, if there's even a hint that something artificial is going on, then brushing off the signs just because they don't fit our usual ideas means we're missing out on one of the biggest moments in human history. We're basically watching first contact unfold in slow motion, seeing new structures pop up in our own solar system, and still, we keep telling ourselves it's nothing. Why? Because the truth is uncomfortable. It challenges everything we thought we knew. Getting this wrong hurts either way. If we jump the gun and call it artificial when it's not, we lose credibility. If we're too skeptical and ignore real evidence, we miss something extraordinary. Right now, the data is muddy. We can't be completely sure with the instruments we have. So we're forced to decide, which mistake are we more willing to make? Do we play it safe and risk missing something huge, or do we stay open and risk chasing shadows? Different scientists answer that question their own way. Some see 3IATLAS and just see a weird comet from another star system, strange, but still just rocks and ice, nothing intentional. Others look at the same thing and sense there could be more to the story. At the very least, they think it's worth a closer look and some tough questions. Both camps matter. The skeptics keep us honest and make sure we don't get carried away. They want hard proof before they buy into wild ideas. The open-minded ones push us to look past what's easy or comfortable, to consider what we might otherwise ignore. That back and forth, skepticism versus curiosity, is good for science, especially when things aren't clear. You don't settle these debates by picking a side and shutting down the other. You keep digging. You build better tools. You plan smarter observations to actually tell the difference between your theories. That's exactly what needs to happen now as 3IATLAS heads toward Jupiter. Observatories all over, across the US, Chile, Hawaii, Spain, and more, are tracking it as closely as possible. Not just with regular telescopes snapping photos, but with infrared to catch heat, radio dishes listening for strange signals, and spectroscopes breaking down what's in the comet's coma to figure out what's turning to gas. The point is to collect enough information that we finally start clearing things up. We want to see if the path changes as it nears Jupiter. Does it act like a normal comet under stress, or does something weird happen? If it breaks apart, do the pieces fly off randomly, or do they move together like someone steering them? We need sharper measurements of those little nudges in speed. Are they just gas jets, or could they mean something more? And of course, we need to listen for anything, radio pings, odd reflections, that might hint at electronics. If 3IATLAS turns out to be just another natural object, that should become obvious soon. As it gets closer to Jupiter and heats up, we'll see more outgassing, more chaos in its path. If it splits, the bits should drift off in all directions, just following the physics of a comet breaking up. Even if some details are new to us, it should all fit with what nature can do. No intention required, just the laws of physics at work. Natural doesn't mean boring. It just means we don't have to invent explanations to make sense of it. But if there's even a hint of something artificial happening with this object, if any of the wild speculation turns out to be grounded in reality, then we're on the brink of a whole new chapter in astronomy and maybe even human history. That's the moment when the search for anomalies gets serious. Scientists start combing through the data for anything that simply can't be chalked up to the usual cosmic processes. Are there signs of non-gravitational acceleration, but without the usual tail of gas and dust you'd expect from an ordinary comet or asteroid? Does the object's motion defy the patterns we know so well, or do fragments break away only to head off in directions that challenge our understanding of physics? Maybe the surface temperature is strangely high or low, inconsistent with what we'd expect from sunlight at that distance. Or perhaps, in a twist straight out of science fiction, we pick up faint radio emissions or radar reflections that hint at metal alloys or structured electronics, rather than just frozen gases and stone. What if telescopes catch glimpses of geometric shapes or repeating patterns, features that would be hard to explain as the result of random, natural processes? Findings like those would send shockwaves through the scientific community and beyond. They demand a level of scrutiny and debate far beyond the norm, and force us all to seriously entertain the possibility that this is no ordinary interstellar rock. Of course, each piece of evidence would have to be picked apart. Nature has a knack for producing the unexpected, and history is full of cases where seemingly inexplicable phenomena eventually found perfectly natural explanations. But at a certain point, enough strangeness starts to tip the scales. The odds shift, and what once seemed like wild speculation, an artificial origin, becomes a serious hypothesis. That's when the urgency ramps up. Researchers and institutions race to secure telescope time, write proposals for new observations, and even discuss ambitious missions to intercept or rendezvous with the object. The stakes suddenly feel higher, and there's a sense that this could be one of those rare moments that changes our collective understanding of the universe. Time, however, is not on our side. 3IATLAS is already on its way out of the inner solar system, moving away from the sun, cooling down and fading into the darkness. Every day it recedes, it becomes harder to observe. The window for meaningful study is closing fast. Within a year or two, it could be so faint that only the largest, most advanced telescopes on Earth, or perhaps only those in space, will even be able to detect it, let alone capture detailed data. If we don't act decisively now, we risk letting this opportunity slip through our fingers, left with nothing but partial data and a host of tantalizing but unresolved questions. The object will continue its silent journey through the void, and we'll be left wondering what we missed. That's why these next several months are absolutely critical. This is likely the one and only chance we'll get to uncover the true nature of 3IATLAS and to understand what it means for our place in the cosmos. Astronomers around the world feel the pressure. They're working overtime, negotiating for precious observing slots, collaborating across continents, and rapidly developing new strategies for data collection and analysis. There's an undercurrent of excitement, but also palpable tension. Everyone realizes the significance of the moment and what could be at stake for science, philosophy, and perhaps even our sense of identity as a species. Even if, after all the scrutiny, 3IATLAS turns out to be a run-of-the-mill comet or asteroid, just another chunk of ice and rock flung from a distant star system, it will still be a scientific triumph. Every interstellar visitor we detect expands our understanding of planetary formation, the dynamics of solar systems, and the processes that scatter material across the galaxy. Each new data point helps us piece together the grand puzzle of how worlds are born and how matter migrates between stars. Science advances by building up large, diverse samples, finding patterns in the chaos, and testing theories against the real universe. If 3IATLAS is natural, it strengthens that foundation and opens the door to even more discoveries in the future. But if the evidence ever points in another direction, if those extraordinary signs of artificiality start to stack up, then everything changes. The realization that something in our solar system might be the product of intelligence, of technology, perhaps even of a civilization beyond Earth, would be the most profound discovery in human history. It would force us to reinterpret our own story, to confront the possibility that we are not alone, and to wonder about the intentions and capabilities of whoever, or whatever, sent this object our way. It would raise questions about communication, about security, about the broader context of life and mind in the universe. Our understanding of ourselves and our future would be transformed. It would spark new fields of research, inspire generations of scientists and thinkers, and perhaps even shift the trajectory of human civilization. And even if the outcome is inconclusive, if our data remains ambiguous and we can't definitively distinguish between a natural and artificial object, that outcome is still deeply meaningful. It highlights the limitations of our current tools and knowledge, underscoring the need for more advanced technology and new strategies to study fleeting, distant visitors. It's a clarion call for investment in better telescopes, faster data analysis, and perhaps even dedicated missions capable of intercepting future interstellar objects as they pass through our cosmic neighborhood. It's a reminder that we're still at the beginning of this journey, and that the universe is constantly offering us challenges and mysteries to solve. Next time, with better resources and preparation, we might finally get the answers we seek, or be ready to ask even bigger questions. The upcoming generation of astronomical surveys is set to revolutionize our understanding of the cosmos, rendering previous efforts almost obsolete in comparison. The Vera Rubin Observatory, currently nearing completion among the Chilean hills, stands as a testament to this leap forward. Once operational, it will methodically scan the entire visible sky every few nights, amassing a trove of data at a rate previously unimaginable. This relentless pace and coverage will grant astronomers the unprecedented ability to detect interstellar objects far earlier than before, giving us the crucial window to train our most powerful telescopes on them, to scrutinize their every detail, and perhaps to catch them before they slip away forever. Simultaneously, new space-based infrared missions are on the horizon, promising to capture the thermal signatures of these cosmic wanderers. By measuring their heat, we'll be able to deduce their true sizes and compositions with far greater accuracy than visible light observations alone could provide. These missions will allow us to distinguish between a small, dark object and a much larger, more reflective one, uncovering the hidden diversity of materials and structures among interstellar visitors. Meanwhile, the spacecraft we're sending to explore asteroids and comets within our own solar system are more than mere technological demonstrations or scientific curiosities. They serve as blueprints, as practice runs for future interception missions that could one day allow us to rendezvous with an object from another star system, to study it up close, to perhaps even bring samples back home. Standing at the threshold of this new era, the sense of anticipation is palpable. We are poised to witness a transformation in how we watch and understand our solar neighborhood. In the coming decades, as detection methods sharpen and our reach expands, we will likely catalog dozens, if not hundreds, of objects born in distant star systems. Each discovery will add a piece to an emerging cosmic puzzle. Patterns will begin to surface. Perhaps certain types of objects are more common, or maybe the diversity will surprise us. What once seemed utterly alien might become familiar, or we may find ourselves confronting phenomena that challenge the very foundations of planetary science. With every new detection, our analytical tools will become more sophisticated, moving us steadily away from speculation and toward real understanding. We may finally reach a point where these visitors are not just fleeting blips in our telescopes, but subjects of rigorous study, revealing whether any among them are more than mere aggregates of rock and ice, perhaps even bearing the subtle fingerprints of processes we have yet to imagine. Yet, within this expanding horizon of knowledge, another, more sobering perspective emerges. As our instruments grow in power and reach, so too does our awareness of our own insignificance. Despite our technological triumphs, we remain in the grand narrative of the universe, little more than background noise, extras rather than protagonists. It's a humbling realization, one that cuts against millennia of human self-regard. For so long, our stories, our philosophies, even our sciences have cast us at the center of things. We have imagined ourselves as uniquely significant, our actions as echoing through eternity, whether judged by gods or by the cold laws of physics. But when an object like 3IATLAS, a visitor from another star, sweeps through our solar system, indifferent to our presence, it delivers a starkly different message. The universe, vast and ancient, is not waiting for us. Our dramas, our aspirations, our anxieties, they are not the main event. The real currents of cosmic history flow far from our tiny planet, unaffected by whether we flourish, falter, or even notice them at all. This realization can be unsettling, even existentially threatening. It challenges the narratives we've built about our own importance, leaving us to wonder what meaning remains if we are not special. Yet, paradoxically, there is liberation in this cosmic anonymity. If we are not being observed or judged, if our every choice does not reverberate on some universal scoreboard, then much of the existential pressure lifts. We are free to define our own values, our own goals, unburdened by the need to measure up to some imagined cosmic standard. Our future becomes something we shape for our own reasons, at our own pace. We can choose to explore, to grow, not because we must prove our worth, but because curiosity and creativity are their own rewards. In this light, our smallness is not a curse but a kind of freedom, permission to simply exist, to make our own meaning in an indifferent universe. Still, for all our philosophical musings, one question continues to haunt us. Are we alone? This longing for connection, for validation that we are not the only thinking beings in the darkness, has driven much of our scientific ambition. We have built immense radio telescopes, listening intently for the faintest sign that someone somewhere is reaching out. We have broadcast our own messages into the void, hopeful that intelligence elsewhere might answer. The prospect of contact, whether it brings hope or fear, has sparked debates about how we should present ourselves, whether to announce our presence boldly or to keep quiet, wary of the unknown. These questions are not mere intellectual exercises. They shape our sense of identity and destiny. The possibility of other minds, other civilizations, reframes our understanding of what it means to be human. If we find that we are but one of countless civilizations, the story of life in the universe becomes richer and more complex, our own role both diminished and ennobled by the vastness of the tapestry. If, on the other hand, we find that we are truly alone, then our responsibility to cherish and protect this fragile spark of consciousness becomes all the greater. As we stand on the brink of new discovery, poised between awe and humility, we are reminded that the universe is not obligated to answer our questions or to care about our aspirations. Yet it is precisely in the asking, in the restless pursuit of knowledge, that we find our meaning. Whether we are observed or ignored, whether we are one among many or the only ones at all, it is our curiosity, our drive to explore, and our willingness to face the unknown that defines us. In the end, perhaps that is enough. Maybe we've been asking the wrong question all along. It's less about, are we alone in the universe? And more about, does anyone, or anything, even care that we're here? And if the answer turns out to be no, if the cosmos is indifferent, if the multitude of possible civilizations out there are uninterested in us, then all those fears and fantasies about first contact or galactic neighbors might just dissolve into irrelevance. Maybe the universe is teeming with activity, civilizations, and intelligence, but the beings involved look at us the way we glance at a distant anthill while hiking, aware perhaps, but uninvested, barely sparing us a fleeting thought. Perhaps some have already come and gone, passing through our solar system with little more than a bored glance, sizing us up and deciding, there's nothing here to see, before moving along. That realization stings in its own way, a kind of cosmic insignificance that can feel like a gut punch. The idea that we're not even interesting enough to warrant curiosity or attention from others is humbling, if not a bit painful. Yet, there's a strange comfort buried in that neglect. If no one cares, there's no threat of invasion, no risk of being exploited for our resources, no cosmic overlords judging our worthiness. We're not on anyone's radar, not under anyone's microscope. In a universe where advanced civilizations could possess technologies beyond our comprehension, being ignored might actually be the safest possible outcome. They're busy with their own concerns, their own trajectories, and we're left to our own devices. Our planet remains our playground, our laboratory, our stage. If we ever do something truly extraordinary, something that echoes across the void, maybe then we'll be noticed. But the burden of becoming remarkable rests with us. We have to earn attention, to become the kind of species that others might finally pause to observe. Until then, our anonymity in the universe is both a shield and a challenge. So where does that leave us, existentially? How do we find purpose or meaning in a universe that's not just silent, but apathetic to our existence? This isn't a new dilemma. Thinkers have wrestled with cosmic indifference for centuries. Philosophers and theologians have long debated whether meaning is bestowed by the universe or whether it's something we must forge for ourselves. Existentialist thought was born from this very predicament, the recognition that the cosmos is indifferent, so it's up to us to create significance through our actions, our choices, our relationships. Yet, what's different now is the sheer scale of our ignorance. and our curiosity. For most of human history, the question of cosmic company was confined to myth, speculation, and dreams. Now, though, we're starting to gather real evidence, fragmentary and uncertain as it may be. The universe is no longer a blank canvas for our fantasies. It's a place we're actually beginning to observe, to measure, to probe. We're hunting for signals, cataloging exoplanets, watching for oddities. We're not just dreamers anymore. We're data collectors, and each new bit of information nudges us closer to the truth, even if that truth is that we're not particularly special. This accumulation of evidence brings with it a new kind of existential unease. As telescopes grow sharper and surveys more comprehensive, we find hints that suggest we may not be alone, or at least that our solar system isn't entirely isolated. If the universe is crowded but disinterested, we face a strange loneliness. The knowledge that there could be 1,000 civilizations out there, all of them looking past us, none of them inclined to reach out. It's not the terror of being invaded, it's the quiet ache of being overlooked. But the pace of discovery is only accelerating. 3IATLAS is just the third confirmed interstellar object to pass through our solar system, but it won't be the last. As our detection technologies improve, we'll identify more and more, dozens, maybe hundreds in the coming years. Most will be mundane, shards of ice, lumps of rock, cosmic debris flung from other suns. Some, though, might not fit our expectations. Some might travel in odd trajectories, display strange behaviors, or appear more engineered than natural. Each anomaly will force us to question our assumptions, to ask if we're truly seeing random debris or evidence of someone else's handiwork. Every new object is a clue in the puzzle. Each discovery gives us a chance to refine our understanding of what's normal and what's extraordinary. Science advances through this slow, deliberate process, not with sudden revelations, but by accumulating data, challenging models, and gradually shifting the odds. What seems impossible today can become plausible tomorrow as the evidence mounts, and as our minds adapt to the emerging reality. But there's an unsettling possibility lurking at the edge of all this. What if the odds eventually flip? What if, after years of incremental progress, the weight of evidence begins to favor the idea that some of these objects are not natural at all, but artificial products of intelligence, not chance? What if we one day detect unmistakable signs of deliberate activity, machines operating in the darkness, alien probes, networks, or infrastructure being quietly established within our own solar system? There is no guidebook for that scenario. SETI has protocols for handling a message from the stars, but nothing prepares us for the realization that we might already be surrounded by silent observers, by artifacts left behind by civilizations who never bothered to announce themselves or seek our permission. The implications of that would ripple through every aspect of our lives: science, philosophy, culture, even religion. We'd have to confront not just the fact that we're not alone, but that we're not the center of anyone's attention and maybe never have been. Would we feel threatened, inspired? Would it drive us to greater heights or plunge us into existential despair? Would we change how we view ourselves, or would we simply carry on, as ants do beneath the feet of indifferent hikers? In the end, the universe's indifference is both a challenge and a freedom. If we want to be noticed, to matter on a cosmic scale, we have to make ourselves worth noticing. The meaning we seek isn't something the universe can give us. It's something we have to build, step by step, discovery by discovery, as we find our place in an unimaginably vast and indifferent cosmos. And perhaps in embracing that challenge, we'll discover a kind of meaning that's uniquely our own. Do we reach out? Should we try sending signals toward Jupiter's Hill radius, just in case someone or something is listening out there? Do we build the tech to get a closer look, try to intercept these objects, study them right up close? Is this a threat we have to defend against, or is it more of an opportunity, one that calls for careful diplomacy, even if the other side hasn't said a word? If this scenario actually happens, these aren't just abstract questions. We're talking real decisions, the kind that shape humanity's future. Right now, the world doesn't have a playbook for something like this. Sure, The United Nations has its Committee on the Peaceful Uses of Outer Space, but they mostly deal with satellites, preventing crashes, cleaning up space junk, keeping an eye on Earth. There's nothing in place for a coordinated global response to evidence of alien megastructures hanging out in our solar system. If it happens, you can bet countries will go it alone, racing to collect intel, make contact, or show off what they can do. That's a recipe for trouble. When everyone acts on their own and tries to get ahead, the risks shoot up. Someone might get impatient, do something reckless, and trigger a response from whoever is out there. Or maybe someone messes with equipment they barely understand and sets off a chain of events nobody saw coming. History hasn't exactly shown us that first contact goes smoothly, especially when the less advanced group is the one doing the discovering. But honestly, it's way too early to panic about our response. We don't even know what we're dealing with yet. Maybe 3IATLAS is just a regular comet with weird timing. Maybe the numbers line up by chance. Maybe as more data rolls in, all the weirdness will fade away and we'll realize there's nothing here except a cosmic oddball. If that's how it plays out, then all this talk about alien infrastructure will just be another wild thought experiment. Or maybe the strange stuff continues. Maybe the data over the next few months shows patterns that don't make sense unless someone is actually arranging objects around Jupiter's Hill radius. If that happens, we're in uncharted territory, facing something that forces us to grow up as a species. Suddenly, we're not alone, we're not special, and we've got to figure out how to move forward in a galaxy that's a lot busier and more complicated than we ever guessed. The answer might already be right there, unfolding in the space around Jupiter, hidden in flight paths, shifts in speed, patterns we're only just starting to notice. We're witnessing something big, maybe the biggest thing humanity's ever seen, or maybe just a really strange comet passing through. The uncertainty is real. The ambiguity is real. How we handle that, balancing skepticism and curiosity, caution and openness, that's going to say a lot about who we are and what we're capable of. 3IATLAS blew past Earth without stopping. That one fact, more than any theory about what it is or where it came from, says something huge. We're not the destination. We're not the focus here. We're just another planet in a system with a giant gas world that's got a magnetic field and some interesting orbital tricks. If there's anyone out there, and if they're watching, they've already shown us where their interests lie. Jupiter matters. Earth doesn't. Not enough to visit. Not enough to investigate. Not even enough to say hello. That's the message staring us in the face, whether we're ready for it or not. That's where things are headed. As 3IATLAS closes in on Jupiter over the next weeks and months, we'll keep collecting data, sharpening what we know and wrestling with what it all means for us, for our future, for our place in a universe that turns out to be a lot less empty and maybe a lot less interested in us than we ever thought. The observations keep rolling in. Telescopes track every move. The data piles up. Somewhere in that mess of numbers and wild guesses, between hard facts and all the things we're just speculating about, the truth is hiding. It's out there, whether it fits our hopes or shatters our assumptions, whether it puts us at ease or shakes us up. It's flying through space at breakneck speed, locked onto its path, carrying answers to questions we barely realized we should ask. And here we are, watching, trying to make sense of something drifting through our corner of the cosmos. We wait, we measure. We debate and argue. We wonder if we're seeing history unfold or if we're just connecting dots that don't mean anything, finding patterns in noise, meaning in what's really just coincidence. But answers are coming. In a few months, we'll know more. Not everything, not even close, but definitely more than we do now. That slow drip of progress, that gradual climb toward understanding, even when the picture is still blurry, that's what science is all about. It's what we do, poking at the universe, trying to figure out what on Earth or off it we're looking at. 3IATLAS is giving us a crash course in cosmic humility, reminding us that space isn't empty, that visitors show up without warning, that maybe we're not the main event, that the real stories might be unfolding out near the big planets, in places we barely think about, in gravitational hideouts we're only just starting to notice. And maybe the biggest lesson, that the question, are we alone, doesn't have a simple answer. Maybe we're not alone, but just ignored. The universe might be buzzing with activity and we're on the sidelines. We're part of the crowd, but so far off to the side that nobody's bothering to wave. That's where things stand. That's what 3IATLAS has shown us, or might have, depending on what the final numbers say. We're right on the edge of understanding, staring at possibilities that are both thrilling and intimidating, waiting to see what comes next. The universe doesn't owe us explanations. It definitely doesn't owe us importance. It just is. Huge, complicated, full of things and maybe beings we're only starting to notice. And here we are, stuck on a little planet orbiting a run-of-the-mill star, trying to figure out our place in all of this. 3IATLAS swept past us without so much as a nod. In that indifference, that cosmic silence where we half hoped for contact, maybe we've learned the universe's most important lesson. We're not the center. We never were. If we can accept that, if we can find meaning anyway, maybe that's what decides whether we make it, whether we hang around long enough to become the kind of civilization someone someday actually thinks is worth stopping for. The real answer to "are we alone?" might just be no, but nobody really cares. And honestly, figuring out how to live with that, how to find meaning in a universe that doesn't care whether we're here or not, could end up being the biggest challenge we face in the next few centuries. Look at 3IATLAS. It passed right by Earth without even slowing down. That single fact, more than any wild guesses about what it is or where it came from, says something big. We're not what it's looking for. We're just another stop in a solar system where Jupiter, with its wild magnetosphere and handy orbit, is way more interesting. If there's anyone, or anything, out there watching, their choices couldn't be clearer. Jupiter gets the attention. Earth doesn't. Not enough to pause, not enough to check out up close, not even enough to give us a nod. That's the message. Whether we like it or not, that's what the path of 3IATLAS tells us. And as 3IATLAS heads toward Jupiter in the coming weeks and months, as we keep tracking it and learning more, we're going to have to face what that message means for us, for our future, and for our place in a universe that might be a lot more crowded than we thought, but still couldn't care less about us.